My name is Emre Güler. I'm a PhD student at Ruhr Universität Bochum in Germany. And I want to talk about research that we have done last year, which is about how to apply fuzzing principles to web applications so that you can find server-side vulnerabilities like SQL injections and PHP command injections, for example. And we focused on PHP web application, but the methods we are going to show are not specific to that language, but to web applications in general. And we picked PHP because most of the web applications are written in that language. The language has come a long way. There's still an association between something written in PHP and being insecure. That is not the case anymore as it used to be like 10 or 20 years ago. But still, I've just looked up like the keyword WordPress for just the last couple of months. And as you can see, there are still a lot of threat actors that are abusing security vulnerabilities to infect websites or the visitors, etc. So security problems are still an issue for PHP and for web applications in general. So while we were writing the paper, we were thinking about what the state of the art is. And when you wanted to do some kind of security analysis of your web application, but you didn't want to do it manually, you had to pick some kind of static analysis tool. And what you usually see with static analysis tools is that they have a lot of false positives. And another issue is even if your static analysis tool reports a bug to you, you still have to find some kind of test case that you can use to actually execute that vulnerable line of code. So you can debug it or write an exploit for it. Both of which is not true for fuzzing, where you have a test case that you can actually execute and exercise that line of code that you want to test against. And also, I mean, this is a fuzzing trick. You guys already know that fuzzing is awesome, but you've already seen also in the other talks that fuzzing has been applied to a lot of different applications. So we know that the principles, the core principles behind fuzzing, they're also applicable to a lot of different applications. So our question was, can we just apply the core principles to web applications, adjust them, and then improve the state of the art, get better bug results and better false positive rates? So to adapt them, we have to adapt them at every stage. So the first stage a fuzzer has to do is mutate, which also implies there's some kind of input space. And for binary applications, the input space is easy. Let's say you have a PNG parser, it's just binary. You can introduce some kind of bit flips. But for web application, of course, this is different, as I will show in the next slide. And then you pick the input and you just execute it. This is a core difference to static analysis tools, which have to faithfully model the PHP language. In a fuzzer, you just execute it and you see real-world behavior behind it. And then you usually see some kind of crash. A crash is a pretty good indicator that a bug is behind it. And also there is some likelihood that it might be a security-related issue if you're interested in security bugs, that is. And in the last step, of course, you get some kind of feedback. Often this is code coverage. But I will show you that for web application, code coverage alone is not enough to explore the whole behavioral space of web applications. So how do we apply all of this to web applications to find like server-side vulnerabilities like SQL injections, etc.? So as for the input space, if you look at binary application, like this is from a PNG parser and this is a PNG file, you can just introduce some kind of bit flips, add new bytes, or merge two inputs together. But for PHP, what's interesting is it looks totally different, right? So the first thing that you notice is you have some kind of target, which is surprising because when you're fuzzing a web application, you assume that is the target, but most web applications consist of multiple PHP files, so you have to select the one that you're fuzzing right now. This is not a problem for us because we are not writing a web crawler that needs to figure this stuff out, but it's a fuzzer that has access to all the source files and the directory structure, etc. But what is actually important here is the key value pairs that are the main part of the input space. So in this case, there is a key called page, and it is set to the value login. So there are two key observations here that we have to know when we want to adapt fuzzing to web application. First of all, the input space is really string heavy. And that is not really common in other fuzzing areas. And fuzzing applications that are string heavy is a bit more difficult because strings have to match completely. And so you can't have partial matches if you're not using something like love intel, etc. And the other key observation is that the input space consists of key and value pairs, which means that you have to find the correct key, the full string, and the correct value, the full string, and you have the correct association between the key and the value. So you can't just introduce any kind of bit flips into the input space and hope to explore the behavioral space. Okay, let's look at an example to see what kind of feedback we had to build in other than code coverage to actually explore all of the lines in the web application. So Atropos is the name of our fuzzer, and on the right is the web application which does the same what I've shown before. It just checks for the get parameter page and if it sets to value. So in our first execution, our fuzzer just sets two random values. One is the key set to ABC, and one is the value set to XYZ. And it executes the web application. And during the execution of the web application, our first advanced feedback mechanism gets activated, which is checking if there were any key accesses which were not provided by the input space. So in this case, the web application or the instrumentation that we've added reports back a feedback saying, hey, there was an access to page, but you have not given me any page. So in the next iteration, our fuzzer can actually say, all right, so here's page, and here's a random input called XYZ. Please execute it again. Now, when we execute it, there is a second feedback mechanism that we have. And this one is interesting because it is just saying, hey, there was a string comparison between the string XYZ and the string login, and it failed. So what we do in this step is basically saying, we randomly pick any XYZ in our input space, and we replace it with the string login. And I note that I said we replace occurrences of XYZ with login, not that we set the value to login. This is an important distinction because as outlined in the red green paper, input to state correspondence is really helpful in this regard. We have fuzzed a JSON parser and an HTTP parsing library, HTTP request library, sorry. And both were implemented in PHP itself. And just using these feedback mechanisms, our fuzzer was able to generate highly structured, correct JSON and HTTP requests, for example. And of course, in the last step, what our fuzzer is now doing is just set page to login, execute it, and our third feedback mechanism, which is plain old code coverage, is telling us that a new line of code was executed. So once we've done this, we've explored, in this case, the full behavioral space of the web application. All lines were covered, but we still don't know how to check if any vulnerable state was reached. We have, for our custom bug oracles that will tell us a vulnerability has been found, we have one key observation, and it's a simple one. It is saying that many of the security-critical PHP functions that can have security vulnerabilities also demand a structured input. So as an example, my SQL query requires an SQL syntax. Unserialized requires a serialized object that is kind of like JSON. Eval expects PHP code, and shell expects some kind of shell command line. All of them have some kind of structure that you have to adhere to. And the other observation is that fuzzers, of course, generating random inputs will unlikely to adhere to this syntax. So if you have a fuzzer-controlled input and that input is unsanitized, that will cause a syntax error. And that is a simple observation, and our runtime bug oracles are based on this observation, basically saying if I know that a fuzzer-controlled input ended up in one of those vulnerable functions and it caused a syntax error, then I can be pretty sure that this is a security vulnerability. And then our bug oracle basically triggers a crash, basically telling the fuzzer, I found an input that is security relevant. So in this example, I've just picked SQL injection, which is the example that pen testers have been using as long as I can remember. Here, there's just an SQL query. A is a secure example where the ID is sanitized, and B is the insecure example, the same one, just with unsanitized ID. And the fuzzer generates a random input, and if we run A, we get no error, it just runs, everything is okay. And if we run B, it actually tells us there is an error with the SQL syntax. And if you look at the input, you see there was an apostrophe in there. So because it was unsanitized, the fuzzer was able to cause an SQL syntax, which shouldn't usually happen. So we can conclude there was a security vulnerability in there. So for our design, if you look at the web application, which is running on top of the PHP interpreter, you might have the idea that, okay, what happens if the web application changes something in the database or changes something in the file system, which will happen sooner or later when the web application gets complex, right? You delete a user entry, for example. The problem is then, of course, that all the test cases that we have found before will not work anymore. They are not reproducible, and this will also impact any test cases that will come after. So how we've solved this is pretty simple. We've put it in a virtual machine. Now, the first idea you get when you hear this is that this must be really slow, and this is fuzzing. It shouldn't be slow. But we've used UNIX, also known as KFL, which has this property that it can execute up to 10,000 snapshot restores per second per CPU core. So there's basically no overhead that is of any relevance for our use case. That is more than enough for us. And the other part of the design is that we've built in our feedback mechanisms, patched it actually into the PHP interpreter itself. We've also built an extension which reports code coverage in any of the other feedbacks. And this is the overall design of Atropos, our fuzzer. So as for the evaluation, we've evaluated against static analysis tools, a bunch of other tools outlined in our paper. But I just want to highlight those because, as you can see, that even Atropos just running on a single core finds more bugs than the state-of-the-art static analysis tools. And with fuzzing, there's usually, to a certain degree, you can scale the performance by just adding more resources to it. And in our case, we've used all the 40 CPU cores that we had on our machine. And as you can see, we nearly found all the bugs in the 3 test suites that we looked at. And what I also want to highlight is that Atropos didn't report a single false positive on the test suites. And the only other tool, the static analysis tool, that also reported 0 false positives is SonarQube, also known as RIPS. But that one also missed nearly half of the bugs. And as in regards to code coverage, we've also increased the code coverage by 46%. And compared to the second best tool, of course, a lot more compared to the other ones. And we've also found a few vulnerabilities. So it looks to be working quite well. And that was from me, and I'm happy to take any questions. Thank you.